Hello everyone, my name is Girish Moodalbail. My role at NVIDIA is to design, develop, and manage SDN networking for GPU accelerated compute. The compute itself can be virtual machines, bare metal servers, Kubernetes pods, and each of them having NVIDIA GPU networks and GPU cards in them. I'm also upstream contributor and maintainer for Oven Kubernetes CNI project. I deal with the OVS and Oven in my day-to-day work. Leah, you want to go introduce yourself?
Hi, my name is Liel Shoshan. I'm a software architect at Mellanox, now NVIDIA, working on cloud accelerations, Kubernetes integration, and switching offloads.
Okay, great. So we're going to talk about how to secure bare metal nodes that form the Kubernetes cluster using oven logical constructs and bump in the wire Smartnic. And in our case, it's going to be Mellanox Bluefield network adapter. So this is going to be the flow of our talk today. We're going to kind of explain as to why deployers are running Kubernetes cluster on VMs, why they should be running the cluster on bare metal nodes. We'll have a quick overview of Oven, and we'll see how Oven control plane runs on the Smartnic, how the data path for Oven gets offloaded to the hardware, and we'll also kind of look at other Smartnic advantages. So deployers have been building Kubernetes clusters in VMs as nodes, and in this model, they actually take an application, containerize it. They run the containerized application inside a pod. The pod itself is running inside a VM, and the VM itself is running on the bare metal box. So there is several layer of fencing, if you will, and the whole reason here is they want to protect the data center from a application which can be compromised. So the reason they do this fencing is because they're not confident about the container security, and the hope is that if an attacker breaks out of the container, they're still trapped inside the VM, and then they don't have access to the bare metal node, and therefore they cannot cause any harm to the data center itself. However, this comes with a huge performance cost for the application. A lot of the hardware resources like the NIC, the GPU has to be virtualized, and this virtualized thing has to be passed down to the VM, and the VM then has to pass down to the container. There's also an hypervisor overhead for the application performance. So the thing is, there's a trade-off. The trade-off between performance and security and isolation. So the deployers kind of tend to err on the side of security, and they don't kind of focus more on the performance because security is of paramount importance. So that need not, however, be the case. With the help from bump in the wire Smartnic and distributed SDN control plane, it's possible that we can get both performance as well as security and isolation. And this kind of moves the trust zone from the hypervisor onto the Smartnic hardware. And we're going to explain how this bump in the wire Smartnic and the distributed SDN control plane enables achieving both performance and not at the same time losing security and isolation for the bare metal nodes. So where we're going with this is that so with the Smartnic and bump and the distributed control plane, it is possible to push all of the ACLs and the firewall rules, if you will, to the Smartnic itself. The pods running on the bare metal, they're totally unaware of this bump in the wire. All the Kubernetes network policies for the pod are implemented on the Smartnic, um, and then the ACLs for the host itself is implemented on the Smartnic. So if an attacker kind of jumps out of the pod and is now on the bare metal host, they cannot flush IP table rules or the NAT rules or any host-based firewall rules because all of the firewall rules are on the Smartnic, which is acts as a bump in the wire thing. So in that way, you can secure the bare metal nodes. So Oven, the distributed SDN control plane, and the Smartnig kind of join hands here together to kind of provide bare metal network security and isolation. So Oven is open source project. It's a distributed SDN control plane that provides network virtualization solution. It's developed by the Open vSwitch community. The GitHub URL here is where you can find the repo for the project. The thing with Oven is that the whole data path for Oven can be offloaded with Mellanox NIC. So obviously with the offloads, you get the reduced CPU utilization, and the CPU can be used for applications. And in addition, we also get increased throughput. Oven can be better explained with with an example and a diagram, and that's what we're going to do next. So in this diagram, you have two things, right? You have a logical topology to your left, and then we have realized that logical topology on the two bare metal nodes. Um, so on the logical topology, it's a very simple logical topology. It's a logical router with two logical switches connected to it, and each logical switch has a logical port attached to it. Logical router is a L3 entity. It provides routing, ECMP, NAT, load balancing, policy-based routing. Logical switch, on the other hand, provides support for ACLs, support for DHCP. It also provides support for load balancing and DNS. The logical port captures the MAC address and IP address. It's where we apply ACLs, and then also it provides anti-spoofing support. So the thing is, the logical port maps to a Kubernetes pod network interface. So the logical port is an API to control the pod's interface attributes. So you kind of apply policies on the logical port. It kind of reflects on the physical on the pod interface on the pod. So um, so on the right side, what we have a two bare metal nodes. And on these nodes, you have a OVS integration bridge called BRInt. This integration bridge implements the whole logical pipeline, the whole Oven logical topology using a OVS pipeline, using OpenFlow tables and flows in those tables. So in this particular diagram here, on node 1, a pod 0 got scheduled. On node 2, pod 1 got scheduled. Pod 0 is connected to the integration bridge through a OVS internal port, P0, and pod 1 is connected to the OVS integration bridge to the internal port, P1. So what we do here is that we associate this physical port with a logical port. And that process is called port binding. And this is one of the important aspects of Oven. What this port binding does is it tells you the physical location of a port for a given logical port. So with that physical location known, now the Oven control plane knows where to send the packet to for a given pod. In this example, when pod 0 wants to talk to pod 1, when the packet arrives on the BRInt, and this BRInt implements the Oven logical topology through OpenFlow tables, it already knows that to send the packet to pod 1, it has to just send it to the node 2's VTEP IP address. And then using OpenFlow flows, it just forwards the packet to that next hop. So the whole logical topology is realized on this integration bridge. And then the physical port or the port binding thing enables that end-to-end connectivity between the ports. So Oven has a collection of daemons that work together to push this logical topology information and the physical location of these ports to each node, and then each node's integration bridge. So in this slide, this slide basically talks about the Oven Kubernetes project. Oven Kubernetes is an open source project contributed or worked on by the Oven community. The GitHub URL for the same is here, as shown in the slide here. It implements container networking spec 0.0.4. It's a layered architecture. At a higher layer, you have Oven Kubernetes CNI, which in turn depends on the Oven, and Oven in turn depends on OVS. So the CNI itself is implemented as a client-server architecture. It's basically a Kubernetes watcher, and it has several set of pods. It kind of takes the Kubernetes resources and then it maps into Avan resources. For example, Kubernetes network policy is mapped into Avan ACLs. Kubernetes cluster services is mapped into Avan load balancer. Kubernetes pods is mapped into logical switch ports, and Kubernetes node is mapped into logical switches. So it watches on these Kubernetes API resources. As and when these API objects appear, it kind of translates that into Avan resources. So the Avan control plane kind of acts on those Avan resources that was created by the Avan CNI, and then converts that into Avan logical flows. And these logical flows are in turn translated into OVS open flow rules on each of the node that forms the Kubernetes cluster. So on the diagram to the right, you see that you kind of explain all the components running at various layers, or on the components of various layers running on various nodes in the Kubernetes cluster. So the whole point here is that to show um, that some of the Avan control plane components, they run on the nodes, and when we move to the Smartnic model, these control plane components will end up running on the Smartnic itself. So in here, you can see that on the host, we had the OVS bridge and the Aman controller, which kind of was adding OpenFlow flows into the OVS bridge, and the Avan CNI component itself running on the host. But when we move to the Smartening model, the entire SDN control plane, the distributed SDN control plane, starts running on the on the Smartnic itself. The Smartnic comes with a ARM core. It has its own OS running on the ARM core, and then all of these control plane components move to that ARM core. Obviously, this kind of provides increased performance and isolation for the bare metal nodes. So this diagram kind of dives deep into how things look like on the Smartnic. So on the Smartnic itself, we have Avan control plane components running, which is Avan controller, and we have OVS components running, which is OVS vSwitch T and OVS DB server. And on the Avan CNI side, we have an agent running, which acts as a Kubernetes watcher, trying to watch on certain Kubernetes resources and then acting on those resources lifecycle. The Avan controller takes the logical flows from the Avan and then translates into the OpenFlow tables and OpenFlow flows, and then kind of creates the data path for the pod. On the bare metal host itself, we have Multus to orchestrate multiple interfaces into the pod, and we have a very basic CNI that takes the next available VF from the PF and then provides it into the pod itself. For every VF in the host, we have a corresponding representer. We have a corresponding control entity on the blue field itself. We call it as a representer. It represents the VF on the host, and we add these representers to the integration bridge. And this representer maps to the logical switch port in the Avan topology. So this is the port binding aspect of the Avan functionality. So when a representer 04 gets added to the BR int, we kind of annotate representer 04 to tell that it belongs to certain logical port. So now anytime we change the logical port's attributes, the representer's attributes change through OpenFlow flows, and therefore the VF2 that is attached to representer 04, it will see that changes. All of these things are being done on the next hop. Next hop, it acts like a next hop switch. It's like a bump in the wire. So all the attributes of the logical port gets reflected on this representer, and then it gets reflected on the VF itself. Um, so that's pretty much what this slide talks to. So this slide basically captures how we can use Avan ACLs to kind of add ACLs at different priorities, and therefore override the ACLs that the tenants themselves configure. So in here, Avan ACLs priority range from 0 all the way up to 32,767. So higher the priority of the ACL, higher will be its precedence. So in the design here, we have all the tenant ACLs being represented with priority less than 10,000. However, all the cloud provider ACLs are at the priority more than 10,000. So therefore, their precedence will be higher as compared to the tenant ACLs. So whenever the Kubernetes network policies are translated to our ACLs, they get priorities in this range. The cloud providers, they can come in on the side and then add their ACLs at a higher level so that they can kind of make sure that the pink tenant here does not somehow talk into the blue tenant, because the cloud provider added ACLs to make sure that such a communication is not possible. In fact, the cloud providers can add ACLs to their own infrastructure services to make sure that the tenant's host or the tenant's pod do not talk to infrastructure services that they're not supposed to talk to. So in this way, using our priority ACLs, we kind of make sure we provide that isolation of between the bare metal host and the data center services and the data center itself. And all of these ACLs, the flows is all offloaded onto the integration bridge, and Liel is going to talk to it in the next set of slides. So then, so in here, what we have done is we have two different bare metal servers, and the bare metal itself is part of our logical topology, and then the Kubernetes cluster also is part of our logical topology. So the pods are kind of connected together within an oven logical topology orchestrated by the oven CNI. On the other hand, the bare metal servers themselves are part of oven logical topology, and the interconnection between them is provided by oven. So in here, the pods, if they want to talk east-west traffic between the pods, is represented through the green color. It's an overlay traffic, and the network policies for this overlay traffic is defined by the Kubernetes network policies. On the other hand, the east-west traffic between the bare metal server itself is achieved through the oven logical topology and using an overlay, and then we'll have oven ACLs define which bare metal host can talk to each other and which bare metal host cannot talk to each other. This is defined by the oven ACLs. See, both the green overlay and the orange overlay, they are transported over the blue underlay. This forms the underlay where the blue fields are all blue fields in the data center. They're all interconnected together, and they form the underlay over which the Geneve tunnel traffic is transported between the pods and between the bare metal server itself. So the red underlay network here is for access to the internet. If these pods want to access to the internet, they kind of exit out of the tunnel or exit out of the oven logical topology through a oven gateway router, where they get source netted into the Bluefield IP, and then now they're on the red underlay and heading towards the internet. The same thing is true for the bare metal server host trying to access internet. So they exit out of their logical topology through a gateway router, oven gateway router, where the source netting happens. The logical topology IP is source netted to the Bluefield underlay IP, and then the packet head towards the internet. So that's this diagram. So here, what we're capturing is how one can provide a multi-tenancy model in a DC using oven distributed control plane and a Smartnic in it. So in here, we have two tenants, a blue tenant and a pink tenant. The blue tenant has a bunch of bare metal servers, which are all interconnected together using an oven logical topology. On top of these bare metal servers, they're running Kubernetes cluster, which is orchestrated by the Oven CNI, and the cluster, the Kubernetes cluster itself is in its own logical topology. Similarly, here for the ping tenant, they have a bunch of bare metal servers in the DC that was assigned to them, and the bare metal servers themselves are connected together using a logical switch and a logical router. And then on those bare metal servers, they have their own Kubernetes cluster running, which is again orchestrated through Oven CNI. As you can see, they all use the overlapping IPs, and and this is all made possible because of the oven virtual topology, and they all exit out to the underlay, and then finally they reach out to the internet. The cloud providers can apply their ACLs on the bare metal, on the Smartnic, to kind of make sure that the blue tenant and the pink tenant are isolated from each other, and they're also isolated from the cloud provider services itself. And the next slide kind of talks to that. So in here, we show a DC networking with TORs and L2 within the TORs, and everything across the TORs is L3. So here you see blue tenant has a bunch of bare metal nodes assigned to it. There's a 4 bare metal nodes assigned to it, and each of the bare metal node has a Bluefield adapter assigned to it. And then these 4 bare metals, they form a VTEP network amongst themselves. There's a concept of trusted zones. So you create this island of bare metal servers with Bluefield on them, and these the Geneva traffic, or the oven traffic only kind of uh, happens or occurs between these set of bare metal nodes. On top of this bare metal node is where we build the Kubernetes cluster, and then they kind of live within this island. Similarly, the pink tenant also has its own island with a set of bare metal servers, with each of them having a blue field associated with it, and they have their own logical topology, and the tunnel is formed only between these 4 pink bare metals. So in that way, there is no interconnect at all between the blue island and the pink island. And then in the same way, the cloud provider services, the cloud provider can provide their services either on the physical network directly, or they can provide it on the oven logical network itself. So in that way, a blue tenant can access some of the services provided by provided by the cloud provider, um, through the logical topology, or directly they exit out to the underlay, and on the underlay they kind of connect to the services running on the physical network itself. Next slide, Liel, can you proceed?
Sure. Thanks, Girish. So in addition to the security enhancement and isolation, this solution also enjoys Datapass hardware offload. This is done using the ASAP Square framework by Mellanox, accelerated switching and packet processing. It's a software and hardware integrated framework which utilizes Mellanox NICs to accelerate and offload the data plane while maintaining the control plane in software. So it minimizes the needed changes in Kubernetes CNI or other SDNs. The solution supports different configuration, SRV, and Virt.io, and it's available both upstream and inbox. It consists of 3 capabilities: classification offload, action offload, and Datapass offload, which are required for switch Datapass offload. So as Girish explained, we worked with Oven control plane, which is based on OVS switch. OVS switch is the most popular virtual switch. It's a flow-based one with many capabilities, among which are Geneva, connection tracking, mirroring, and more. And there are many multiple control planes that are built on top of it. OVN is an example for that. It has it has a user space module and a kernel space module. And in the regular configuration, each pod is assigned a VTH, a Paravirt interface. So in the traditional model, the first packet of a flow will go up to the user space. There it will be processed and sent, and then a suitable rule will be inserted to the kernel. So the next packets of the same flow will go directly to the kernel without going through the user space. with ConnectX hardware offload, this rule will not only be inserted to the kernel, but also to the hardware, to the ConnectX embedded switch. In this case, the next packets of a flow will not go to the CPU at all and will just be processed in the hardware. So this way, we keep the first packet miss architecture by using an additional hardware layer, which is the embedded switch, which is located on the NIC. Each pod is assigned an SRAV virtual function. And while the controller or the user inserts the policies by using OVS OpenFlow rules, these rules are offloaded to the hardware in a transparent way using Linux TC rules. Packets are being processed by the NIC, and therefore there is no host CPU consumption, and we increase throughput and decrease latency drastically. The ASAP Square has many benefits. It achieves uncompromised performance. It saves CPU. Using the Smartnic, you can achieve also full isolation, and it facilitates a solution for both bare metal and virtualized clouds. So if for virtualized cloud, then both network virtualization and storage virtualization were traditionally running in the hypervisor, using ConnectX, we can offload the network data plane by leveraging the ASAP Square framework. When we use Bluefield, the Smartnic as a bump in a wire, also the control plane of the switch can run on the Smartnic, on the ARM cores, as well as the storage virtualization and other security services. This is also true for bare metal servers. So I'll summarize. Bare metal clouds raises the demand for network isolation since the host is no longer trusted. Network isolation can be achieved by using a dedicated hardware, which sits in front of the host. We use Bluefield Smartnic as a bump in the wire to run OVN control plane in a secured way by running both the virtual switch and the utilities configuring it on the NIC. We also leverage the ASAP Square framework in order to achieve Datapass hardware offload, which resulted in both drastic reduction in host CPU consumption and enhanced performance.
Thank you, everyone.